Okay, so we are today going to start by proving this theorem. So V is a vector space and these ui's u1 u2 all the way up to un, these ui's are subspaces of V such that V is their internal direct sum. We have to prove that V is isomorphic to the external direct sum of these subspaces, because if you can treat the subspaces as vector spaces. They are, after all, vector spaces in their own right. So we can form the external direct sum of these spaces. So we have to prove that V is isomorphic to that external direct sum. Let us start the proof by defining the function itself. We define a function t from V into the external direct sum of these subspaces as follows. Let small b be any vector in capital V, since V is the internal direct sum of u1, u2, etc. un there exist unique vectors u1 belonging to u1, u2 belonging to u2, and so on, un belonging to un, such that V is their sum. We define the T image of V to be this element. Clearly, this n tuple belongs to the external direct sum, because as I said, the external direct sum is nothing but the Cartesian product of these sets. I mean these vector spaces, these subspaces. So the output of this function for every input actually belongs to the second set. Also, uniqueness of these ui's implies that the function t is well defined. Note that also uniqueness of the ui's implies that T is well defined. Okay. Note that T is onto because for any element, say W1, W2, etc., Wn belonging to the external direct sum, we have this vector in V, because you see the Wi's belong to the corresponding Ui's, but the Ui's are all subspaces of V. So after all the Wi's are in V, so their sum is a vector in V, such that the T image of this vector is nothing but that n-tuple. Okay. Next we show that T is a vector space homomorphism. So for that, let V and W, we can take in fact anything, because these are after all variables, V and W in V. Then there exist unique vectors, because V is the internal direct sum of the Ui's. For that we will get vectors like before. So there exist unique vectors Ui and Wi belonging to Ui for I varying from 1 to n, such that and do not confuse these Wi's with these things. Okay, we used this n-tuple to show that T is onto. That is over. We have shown that T is onto. Now again we can use these symbols for some other purpose. Note that V plus W, by using the fact that our vector space V is an abelian group under addition. So addition is commutative as well as associative. Using these things, using these facts, we can write V plus W like this: U1 plus W1 plus u2 plus w2 plus un plus wn, where u1 plus w1 belongs to u1, u2 plus w2 belongs to u2, and like that un plus w1 belongs to un. So the representation of v plus w as a sum of vectors from the ui's is this, and because of the fact that v is an internal direct sum of the ui's, this representation actually is unique because there can be only one such representation. And why is ui plus wi in capital Ui? That is because capital Ui is itself a subspace, and ui and wi are coming from ui, so their sum will belong to capital Ui. Hence, by the definition of our function t, this will be equal to and now you use the definition of addition in the internal direct sum, because that itself is a vector space, so it has its own addition of vectors, and that is nothing but we do it component wise. So and this is Vt, whereas this one is Wt. Also, for any scalar alpha in the underlying field, we could have mentioned that V is a vector space over some field F, but there is really no need to do that. There is since V is a vector space, there is an underlying field of scalars. So from there we are choosing one scalar alpha. We have alpha v equal to alpha u1 plus, we are using one of the vector space axioms because we are multiplying the sum, this sum by alpha, so the first of those four axioms we are using here. And we are writing alpha v as this. Where again, like before, alpha u1 belongs to u1, alpha u2 belongs to u2, and so on. Alpha un belongs to un. Thus, if we now apply the function t on the vector alpha v, then by the definition of t it will be this. that is equal to alpha times which is nothing but this. So we have shown that T respects addition and multiplication by scalars. So T is a vector space homomorphism, hence T is a homomorphism. So T is an onto homomorphism, and the only thing left for us to show is now that T is also one-to-one. So we look at the kernel of T. Let X be any vector in the kernel of T. Since the domain of T is capital V, so X is after all a vector in capital V. So just like every element of capital V, X is also expressible as a sum of vectors from the capital Ui's, those subspaces. Let X equal to X1 plus X2, there is one such representation of X as a sum of vectors from Ui, where, and that representation is unique, where Xi belongs to Ui for I varying from 1 to n. Then, since X belongs to the kernel of T, so the T image of X will be the zero element in the second space, which is the external direct sum of the Ui's. So the zero element in that is this. The first one is the zero vector in U1, the second one is the zero vector in U2. Actually, all of them are going to be the zero vector in V, because all the Ui's are subspaces of V. So this is xt, but by the definition of xt, because this is the representation of X as a sum of vectors from Ui, we get this. Which implies xi equal to 0 for all I lying between 1 and n. Thus, X itself is 0, because X is the sum of all the xi's, which each one of them is 0, so X is 0. So the kernel of T consists of only the 0 vector in V. Hence, the kernel of T consists of only the 0 vector in V. This implies T is 1 to 1. Thus, T is an isomorphism of V onto this external direct sum. So V is isomorphic to the external direct sum, and we see that if we have a number of subspaces of a vector space V such that V is the internal direct sum of these subspaces, then there is no real distinction between the internal direct sum and the external direct sum of the subspaces. So that is why so the proof ends here, but after that we have these remarks. Because of the isomorphism, proved in the above theorem, we shall henceforth merely refer to a direct sum. Not qualifying that it be internal or external. So here the results of this section end. Let us now look at the exercises. Exercise 1 is something we have already used. Anyway, let us prove it. It's an application of that. I think it's lemma 411, if I am correct, which allows us to do some simple calculations in a vector space. It's that result. It's an application of that result. In a vector space, show that alpha times v minus w is alpha v minus alpha w, where of course alpha is a scalar and v and w are vectors. Although we are not going to mention explicitly which axioms we are using to carry out this calculation and get the final form of this result, but while writing the things we will of course say what we are doing. We have alpha times v minus w. V minus w is nothing but v plus minus w. Okay, in the abelian group, that is the vector space from where in which all these things are happening. So there v minus w is v plus minus w, that is the sum of v and the additive inverse of w. Then you use the first vector space axiom and write this as alpha v plus alpha times minus w. In the next step, we use that result that I was talking about right now, which allows us to do some simple calculations in a vector space. One part of that result says that minus w is the same as minus 1 times w, where minus 1 is the additive inverse of the field element 1. Then you use one other, I think the third axiom in that list of 4 axioms of a vector space, to write the second term as this. Then in the next step, we use the fact that multiplication is commutative in the field, that is while multiplying two scalars we can change the order also. So we can write alpha times minus 1 as minus 1 times alpha. Again you use the third axiom and have this. Once more you use that lemma 411 to write this as alpha v plus minus of alpha w, which again means alpha v minus alpha w. So that's how we get the calculation. Then exercise 2. Prove that the vector spaces in example 414 and example 412 are isomorphic. So let us recall what those vector spaces were. In example 414, let us first see what we had in example 412. In example 412, we had this vector space Fn, which is the space of all n tuples of field elements, where addition and multiplication by scalars are defined component wise. And in example 414, we had the vector space Vn, which is the space of all polynomials in x over f of degree at most n minus 1, including the zero polynomial. We have to say it separately because the zero polynomial, we haven't defined any degree for it. Okay. Now we are going to define a function from Fn to Vn and show that it's an isomorphism, just like what we did here. Like this. Define T from, you can either define it from Fn into Vn or from Vn into Fn, it does not matter really. By our domain now is Fn, so the inputs will be n tuples of field elements and outputs will be polynomials. For convenience, let us denote it slightly differently. We start with 0 and end with n minus 1. So the alpha i's are field elements, so that this is an element in Fn. We define it to be equal to this polynomial, which is either the 0 polynomial or is a polynomial over f of degree n. That is, it is an element in Vn. Clearly, T is well defined. Since an n-tuple has only one representation, so there is no question of having possibly different outputs for the single input, for one single input. So that's why T is well defined. Also, T is obviously onto, which you can clearly see. Any polynomial in Vn looks like this, and which will obviously come from one such n-tuple. So the function T is onto. We now show first of all that T is a homomorphism, and then we show that it is one-to-one by showing that its kernel has only the 0 element. So for that, let this be two n-tuples in Fn. Oh, and let us consider another scalar also, and alpha is in F. Then what happens when we add them and apply T on that sum? This becomes alpha naught plus beta naught. You can see that we are almost doing whatever we did in the proof of that last result, Theorem 412. It's almost like that, similar. So this is the polynomial alpha naught plus beta naught plus alpha 1 plus beta 1 x plus, if we chose to write one more term, it would be alpha 2 plus beta 2 x square. which by the definition of addition in Vn is this. Class So the first one is the T image of this tuple, and the second one of course is the T image of the other tuple. So T respects addition, and this is equal to alpha alpha naught plus alpha alpha 1 x and so on. The last term is alpha alpha n minus 1 x to the power n minus 1, which is alpha times and that is alpha times the T image of this tuple. Thus T is a homomorphism. So next we have to show T is 1 to 1. So let gamma naught, gamma 1, etc., gamma n minus 1 belong to the kernel of T. Then kernel of okay. So this element, this tuple will be mapped onto the 0 vector in the second space, that is the Vn. So the 0 vector in Vn is the 0 polynomial over F. Which is equal to, by the definition of T, this polynomial. Now by the definition of equality of two polynomials, this polynomial equals the 0 polynomial if and only if all the coefficients are 0. So which implies these are all 0. these are all 0 means the element, this n tuple is the 0 tuple, which is the 0 element in Fn. So we directly write hence the kernel of T consists of only the 0 vector. I should perhaps write in words. In Fn, which implies that T is 1 to 1 and all the usual things. T is thus an isomorphism of Fn onto Vn. Hence Fn is isomorphic to V. Looking at the result in Theorem 412 and also this solution, you may think that there is something, the fact that these vector spaces are isomorphic, that has something to do with this n, that number, and in fact that is true. We will show that there is something called the dimension of a vector space, and two vector spaces are isomorphic if and only if they have the same dimension, provided that dimension is finite. Okay, for infinite dimensions also we are not going to make any statement about that, okay, at least in this book. Two finite dimensional vector spaces are isomorphic if and only if they have the same dimension. We will see the notion of dimension in the coming in the next section. Okay, so let us now see exercise 3. Prove that the kernel, oh, we did not prove it, okay, in the text we did not prove it. Prove that the kernel of a homomorphism is a subspace. Maybe we only mentioned that it can be proved that it's a subspace. I can't really remember if I did it already or not. So I will do it once again here in this solution. It may be a repetition. Let U and V be vector spaces over some field F. Let T be a function from U to V, and let that be a homomorphism with kernel W. So let us briefly recall. W is the subset of U consisting of those vectors that are mapped onto the zero vector in V by T. We need to prove that W is a subspace of U. Since zero T is equal to 0, where you should understand that this is the zero element in U and this is the zero element in V. We already know that any homomorphism maps the zero element of the domain space to the zero element of that other space. So we have 0 belonging to W. The zero element in U belongs to W, and thus W is non-empty. So W is a non-empty subset of U. Now let W1 and W2 be two elements in W and alpha be a scalar. Since W1 and W2 are elements in the kernel, so each one of them is mapped onto the zero element of V by capital T. So W1T is 0 and W2T is also 0. Hence, what happens when we apply T to their sum? Because T is a homomorphism, so this is W1T plus W2T, both are 0, so we get 0. And one more thing is this: what happens when we apply T to alpha W1? Again, because T is a homomorphism, this is alpha times W1T, which is alpha 0. Now alpha 0 is 0, and this fact is again coming from that fundamental lemma 411. You multiply the zero vector by any scalar, you get the zero vector. Hence, both W1 plus W2 and alpha W1 belong to W. This implies, by a previous result, by that criterion for deciding when a non-empty subset in a vector space is a subspace, by that result, W is a subspace of U. So that completes the solution. Exercise 4 has two parts. A. If F is the field of real numbers, show that the set of real valued continuous functions. On the closed interval zero comma, well, let me refill, running out of ink. Closed interval 0 comma 1 forms a vector space over F. So that is part A. Continuous, the vector space of continuous functions. And in part B, we will look at vector space of infinitely differentiable functions. B show that those functions in part A for which the nth derivatives exist. For all positive integral values of n. That means these are functions which you can differentiate as many times as you want. Form a subspace. Now I am going to refer to some results from analysis 1 by Terence Tao. These are results which you already know from calculus, so you can give appropriate references from the book that you have followed while you came across these results. It may be any calculus book, it may be a real analysis book, whatever it is. We are just going to use some familiar results about real valued continuous and differentiable functions. So the references I will be using will be from analysis by Tao, which I usually use. And because of that, the solutions will just be some one or two lines where we mention that it follows from that result. It follows from proposition 949. Okay, that is fine, but What is it that we have to prove here? The set we are dealing with here is the set of all real valued functions, that is functions which look like this on the closed unit interval that are continuous. And the operations we will be using in this space are ordinary addition and multiplication of a real valued function by a real number. I say ordinary because it's something very easy. Say you have two functions like this, which are of course both continuous. Then their sum is also a function whose definition is this. Fx plus g of x. Very straightforward. And if alpha is a real number, then alpha f is again one such function, which you can probably guess what we are going to write here. Alpha f x is defined to be alpha times f of x. This is ordinary addition of real numbers because f of x and g of x are both real numbers. Just like that, alpha and f of x are real numbers, so this is ordinary multiplication of real numbers. Now, this proposition says that when we add two such continuous functions, the result is again a continuous function. And when we multiply a continuous function by a scalar, then the result is again a continuous function. And you can of course also verify the other axioms that you need to verify in order to show that this set is a vector space. So that's why instead of writing all those things, I am just simply writing it follows from proposition 949, and this is how it follows. Now in part B, we have those functions that can be differentiated as many times as we want. In particular, because they are differentiable ones, so from a well-known result from calculus, they are also continuous. Differentiable functions are continuous. So that's why the set we have in part B is a subset of the set in part A. Moreover, when we add two such functions and multiply one such function by a scalar, differentiability any number of times it stays intact. Okay, so for that we are going to write, and that is why it will be a subspace of the space in part A. These spaces are very important in analysis. Proposition 10.1.10 in the 10th chapter we treat differentiability in Gauss analysis, shows that the functions in this part form a subset of the set of functions in part A. So this result just says that differentiable functions are continuous. Also, from Theorem 10.1.13, it follows that the functions here form a vector space. Under the usual operations on real valued functions, that means addition of functions, multiplication of a function by a scalar. So that is why the functions here form a subspace of the functions in part A, and that completes the solution. And let us see one more. Exercise 5. Just like the previous one, it also has parts. Part A. Let F be the field of real numbers and let B be the set of all sequences. Let be the set of all sequences A1, A2, etc. Sequences means infinite sequences, which which the author is writing as an infinite tuple, a vector having infinitely many components. It does not really matter how you write it or how you interpret it, as a vector or as just a sequence, an ordered list of real numbers. The thing does not change, where of course all the components, all the AIs are in F, they are all real numbers. Where equality addition and multiplication by Herstein is calling it scalar multiplication itself. Okay. Are defined component wise. If you really think of this as the elements in this set as tuples, infinite tuples, then it is somewhat like Fn. Only thing is that the number of components here is infinity. Okay, so that's why we have infinite sequences of real numbers instead of having vectors with finitely many components. So what is it that we have to do here? Do we have to show that this is a vector space? Yes. I think I forgot to write the complete this part A. I haven't written it. Let F be the field of real numbers and V be the set of all sequences where equality, addition and scalar multiplication are defined component wise. Show that V is a vector space. So that is part A. Then part B, let W be the subset etc. AN subset of those sequences in V which are convergent to 0. We have many different types of sequences of real numbers. From analysis we know that some of them are convergent, some of them are not. So W is the subset of subset of V consisting of those sequences that are convergent and where the limits are all equal to 0. Prove that W is a subspace of V. And there is a part C also, which is start. It comes with an asterisk. Let U be the set of those sequences in V for which the series is convergent. This infinite series. This sum is finite. Same thing, it means that the series is convergent. Prove that U is a subspace of V, just like W. And is contained in W. Okay, so let us see the solution. Part A is extremely straightforward. Just like how you would show that Fn is a vector space, exactly similarly you have to show that this is also a vector space, because there also in Fn equality, addition and multiplication were defined component wise. So all we will be doing when we verify that Fn is a vector space is that we will be dealing with n number of calculations in the field. In each component we are doing field calculation. That same thing we will be doing here with infinitely many field calculations. So that's just it. So we simply write it's straightforward, and it actually is straightforward. Only the number of components is infinity. It's very large. Everything else is truly happening inside the field only. And so the thing here is that you don't even have to go through all the details by writing them down. You try to see them mentally. If you don't get it very easily, that means there is some problem with your understanding of the concept of vector spaces itself. So you please try to do that. For your help, compare with example 412, that is where we have the vector space Fn. So that is just part A. Okay, in part B, so here again we will be using results from analysis 7 to 6 tau says that for any sequence, what? Oh, this is not part B. What the hell am I doing? In part B, we have to show that convergent sequences which are converging to 0, they form a subspace, and this one this follows from theorem 6.1.19. In Tau's analysis, actually we have completed chapter 5. So we are about to start chapter 6, where we develop the theory of real sequences. So there we will come across this. In fact, it's there in the first section itself, this result. What will it say? It will just simply say that if two sequences are convergent, then their sum is also a convergent sequence. Product of two convergent sequences is again convergent, like that. So from there it will easily follow that W is a subspace of C. And now we come to part C. So here corollary 7 to 6. In chapter 7 we have the theory of infinite series of real numbers. Says that for any sequence in U, that is any sequence for which this series is convergent, the limit of the nth term, this is a result that you probably already know from analysis, nth term should converge to 0. From this, it's easy to show that the limit of AI is also 0. You just apply the definition of limit, use the fact that the limit of the sequence AI square is 0. From that itself you will be able to show that this limit is also 0. Hence U is contained in W. Now we have to show that U is a subspace. For that we have to do some things. Now let us consider two sequences in U. So for these sequences the corresponding series are convergent, and also let us take a scalar alpha in F. Then the space U, we haven't shown yet that it's a space, we are going to show that it's a space. This space has a name, it's called the space of square summable sequences of real numbers. Then we will come across these spaces when we at some stage study functional analysis, where we deal with vector spaces which also have a topology on them, so that the algebraic and the topological structure are somehow related. Topological vector spaces, mainly infinite dimensional. Then this and topological vector spaces, aside from the fact that they are mathematically very interesting, they have applications. Applications means their theory itself was developed in order to apply it to develop a mathematical theory of quantum mechanics. These are finite, where you study infinite dimensional Banach spaces and Hilbert spaces by Cauchy-Schwarz inequality, which is a well-known inequality. For this you can see exercise 12.1.5 in Tau's analysis, or you can look this up on the net also. We have something like this: AIBI, where I varies from 1 to n, okay, is less than or equal to the square root of summation AI square times the square root of summation bi square, where in each case I is varying from 1 to n. Note that here we are not dealing with infinite series, here we are dealing with finite sums, and this is true for every positive integer n. We are doing this in order to see what happens to the partial sums of the series, this series, which is of course an infinite series. This inequality can be used to gauge those sums. For every positive integer n. Okay, so now we can use these inequalities to do a calculation. Hence, what happens to this ai plus bi whole square as I varies from 1 to n? First of all, because this is a finite sum and we can expand this using our familiar formula a plus b whole square, so we get an expression like this: 2 times summation ai bi after rearranging all the things bi square, where I varies from 1 to n. Okay, now this is a real number, this middle term. Any real number is less than or equal to its own absolute value. So this is less than or equal to ai bi I varies from 1 to n plus summation bi square I varies from 1 to n. Now we can use this inequality. So we further have this thing less than or equal to n times bi square this plus summation bi square I equal to 1 to n. And this is also true for every positive integer n. Now what can we say from this? Note that this is one term in the sequence of partial sums for this infinite series. Oh, sorry, infinity. Obviously, and we are dealing with a series of non-negative real numbers because we have square here. So this series is convergent if and only if, from a resultant analysis, the sequence of partial sums is bounded above. Now this is nth term, which is less than or equal to this. We have got an expression where there are nth terms of the partial sums of these two series. This and this. We know that these are convergent and these are also series of non-negative real numbers. So these terms are bounded above by some upper bound. So this inequality shows that the sequence of partial sums for this series is also bounded from above, and that's why this series is convergent. Thus, thus, or in fact, instead of writing all those things, we just directly write thus. Since I have already explained this, summation ai plus bi whole square, this is finite. That is, this is finite means what? The sum of these two sequences is again in U. Okay, so U is closed under addition. Similarly, we can show that alpha, I think we considered one scalar also alpha. This belongs to U. Thus, U is a subspace of V. Okay, and here the solution ends. So we stop the video here itself. We will continue with the other exercises in the next video. So until then, this is me, Lucifer, from a mathematical room. Have a nice night.